and welcome. Eamon Darcy is my name. I'm the founder and operator of Quecwans, the Quantum Education Centre of West Australia. And wow, we're up to video lesson 7. And this is quantum games. And you may be thinking, oh, Eamon, this series of 10-minute presentations is supposed to teach me quantum physics and quantum computing. I don't want to play games, but you won't be, because there's a huge initiative out of the States at the moment about learning quantum computing by playing quantum games. And because I've only got 10 minutes, I'm going to focus on only one game, very famous, called the Peres-Mermin. And it shows a game that you can't win every time classically, and a game that you win every time quantumly. So it's very exciting. When people ask me how much faster is a quantum computer and things like that, I normally say, look, in some operations, it literally is millions of times faster and quicker, but that's not the point. It can actually do programs that are logically impossible, and I'm going to show you today. Okay, so before I start, let's have a quick recap on the 7 lessons to date. First of all, our first lesson was on superposition, which it was just amazing, all emanating from the double slit, a quantum particle that you're composed of, that everything is composed of, actually is in a very strange state of what we call wave-particle duality. It's a probability wave and an actual particle at the same time. And this was proven and everybody agreed with it. And we now call that superposition. And whilst a quantum particle is in superposition, it can do many, many computations at the one time. Whereas a bit in a normal digital computer is on or off, a superposition, a qubit, can be on and off in a million different states between 0 and 1. Then lesson 2 was entanglement. So not only is a quantum particle so much more efficient at computation, with superposition, you can actually link them all together in a magical way. Because with quantum particles, you can entangle them, put one on the moon, one on Earth, and as soon as you move one a little bit to the left, the one on the moon moves a little bit to the left. No one knows how that happens, but we can actually harness that power. Then lesson 3, I spoke about the interpretation. So what's going on with superposition and entanglement? The reality is we don't know, but we do have interpretations of what's going on. Interpretations like the Copenhagen, which believes in the collapse of the wave function. And then you've got the many worlds interpretation by Hugh Everett in about the 1940s, 50s. And he was laughed off the park. He was saying that when there's an observer of a quantum particle, you automatically become entangled. And the wave function never collapses. So what that means is that the wave is only collapsing in certain areas. So when it collapses, it forms a new world. And then one thinks about how many worlds there must be. A world where, the Nazis won World War II and 9/11 didn't happen, and all of those scenarios. So it is amazing, and it's very out there. But so is the Copenhagen. When people say, oh my God, how could you possibly believe in the many worlds, which lots of scientists do, I always say, well, the Copenhagen is just as mysterious. Okay, lesson 4 was the basics of linear algebra. When we have this superposition and the quantum particle is doing many computations, how can we keep control of it? Because it's so much more complex than just an on-off. And we basically do this through linear algebra. So that lesson taught you how to multiply 2 matrices together. And there's a few rules you have to learn. And it really After that, it's just learning functions and being able to apply them. Now, lesson 5 was a very important one, the block sphere, which is the way we visually represent this state of superposition. So instead of it being an on-off switch, it's a huge globe, a huge sphere with on and off being at the top and at the bottom, and all the locations in between are referenceable by a quantum computer. So again, very exciting. It's the visual display. Behind that is the linear algebra that's allowing us to go to different points. And then behind that, there's the physical interaction on the superposition, where we send microwave pulses to change the physical state of the superposition. And then quantum gates, again, this is the visual representation. I took you onto a real quantum computer, the IBM Q experience, where we actually can very easily drag and drop and create our own quantum algorithms, which we did, and then run them on a real quantum computer around the world, which we did. So we learned a bit about quantum gates and how easy it was to put a qubit into superposition and then to entangle it. There's just a couple of gates which you drag and drop. A great way to start learning, and then IBM give all the tuition you could possibly need. And today we're talking about the quantum games. So let's carry on. Okay, let me set my timer and away we go. 10 minutes starts now. Yeah, learning quantum computer by playing quantum games is a big thing. It's a US initiative. CalTech and Google AI are getting involved. You can go to that link or just Google Quantime, Quantime, and that'll get you to heaps of games, all aimed at high school children and above, because they are very mysterious. And I'm going to talk about one incredibly mysterious game, the Peres-Mermin magic square. I'm going to tell you what happens in the classical world. I nearly said the real world. I stopped myself from doing that. The real world is the quantum realm. That's the real world. The classical world is what we perceive in our macro level. So millions and millions of atoms at any one time we touch and things like that, but that's not the real world. The real world is the quantum world. 8 minutes 52. Okay, so I'm going to quickly teach you the game, and CalTech and Quantime call it zeros and ones, but it is the Peres-Mermin. It's exactly the same. And if you look in the top right-hand corner, you can see a 3x3, like a tic-tac-toe or Norton crosses board, and it's played with ones and zeros. And you have 2 teams and a referee. Now, the 2 teams need to work together to win the game. And the referee is just there to adjudicate and to make sure that the rules have been followed. Now, there's 2 teams, the blue and the red team. The blue can only fill up the rows. So you see the red block here. The blue team can only do the rows, and the number of ones must be even. So you can see the top one is 0, 0, 0. So that counts as 0, which is even. The second option they have, because there's only 4 combinations they can play. For blue, this is. You've got 0, 1, 1, adds up to 2, 1, 0, 1, adds up to 2, 1, 1, 0, adds up to 2. So they're the 4 combinations blue can use. Red, on the other hand, has to do the columns, and its numbers have to be odd. Now, they're the total rules. The 2 teams can collaborate and work out a strategy before the game, but as soon as the referee says start, then they can no longer operate or know what the other one's doing. The purpose of the game is to get the overlapping square, which is the row from blue and the column from red. There's always, in a 3x3 matrix, there's always going to be one square where they overlap, and they need to get the same number on that square, be it 0 or 1. So if they they could just say, look, I'll do 0, 0, 0, and I'll put it in the top row. You do 0, 1, 0, and we'll always match. And that would be the way it would be great, except for the fact that what happens is the blue team and the red team have no control over which row or which column they put their 3 digits in. That comes down to the referee. So the referee will say to the blue, have you got your row ready? And they'll say yes. And then the referee will roll a die between 1 and 3 or run a program, whichever way. And wherever it is, if it's 1, 2, or 3, if it's 1, the referee places that row on the top. If it's 2, he puts it in the middle. And if it's 3, he puts it in the bottom. And the same process with the red team and their columns. If he rolls a 1, he'll put the column in the left-hand column. If he rolls a 2, it'll be the middle column. And if he rolls a 3, it'll be in the right-hand column. So no matter what happens before the game starts, the 2 teams aren't in control of where they're going to place their row and their column. So what does this mean? Well, spoiler, there's always you can see in the bottom right-hand corner, there's always going to be one place where if you put a 0, it'll stuff up the rows, or if you put a 1, it will stuff up the column. The rule of being odd and even will be broken. So the blue and red teams can only win 8/9 of the time. And that's just a logical fact. So if they play 4 games, they're already down to only a 62% chance of winning. That's 8/9 to the exponent 4. And the same with, if you play n games. Now, if you play just 24 games, so I'm saying n equals 24, so 8/9 to the 24, it mightn't sound much, but it's less than a 1 in 1,000 chance. So after 4 rounds, you've just got about a 50-50 chance of winning every time. But when you get to 24 rounds, it's less than 1 in 1,000. And I had a big worldwide games night where we played this game in Malaysia, Zimbabwe, India, Australia, England, and everybody played the game. And lots of the people, had no knowledge of quantum computers. They just played the game. I've only got 3 minutes left. They just played the game, and they had 1 referee, and the other 2 were players. And we only played 4 games, and we were hit it off on 50%. So you can see that there's no way you can win in the long run. However, a quantum program, and one I may say that my associate and I have just written a Qiskit and a Python code that will run this program, the quantum computer will win this game every time. Now, I've got 2 minutes, 20 seconds to explain why it wins it. And again, remember quantum entanglement was weird? Well, there's another thing called quantum contextuality. And what that means is that a quantum particle has no well-defined, clearly defined properties. And if you measure it in a different way, it will fundamentally, empirically be different from if you measure it in other ways. Now, to give you a classical analogy, isn't that a beautiful graphic on the right? But it's like, if I asked you, what car is it? If you measured it by looking at the fuel injection and the aerodynamics, it would empirically be a BMW. But that same car, if you measured by the suspension and the power steering, it would actually be a Porsche. And I know that doesn't make any sense, but that's what's happening in this world, in the quantum world. So it means that if you've got a particle, if you measure it by its angular momentum and its energy, and then if you measure it with its orbital momentum and the magnetic moment, it will actually say this particle is either or. It's unbelievable. Nothing in the digital world, in the Newtonian physics, works that way. How can it be that the empirical fundamental properties of an object change if you measure them differently? What does this mean for the game? It means that if I measure the square along what are called the commuting observables, which is just the measurement, if you measure it in a row, and then if you measure it by the column, by the commuting observables in the column, you will get both answers at once. The object, the quantum object, oh, there goes my timer. The quantum object can be -1 and +1. It can be 0 or 1 at the same time, depending on how you measure it. And if you measure it with a row, it will equal the same thing as if you measure it by the column. And that is just amazing. Okay, everybody, I hope you've enjoyed this and learned a little bit quantum contextuality. Please look it up and do other research. I will help you, provide you whatever links or you need. Please subscribe to my Quecwa YouTube channel. It really does help, and like the video. Video lesson 8 is on quantum teleportation. It's a beauty. See you then. Bye.